All right, 4.2 is about prime and composite numbers. You've heard those words before. The words prime and composite. I'm not going to ask you right now what they are, but have you heard them?
Yes.
Yes, we've heard them before. Good. All right, so let's start, and we're going to go in and talk about them one at a time. The first one we're going to talk about is prime. So a number is considered prime if it has two positive divisors. Exactly two. Not more, not fewer. Okay, so you guys know what a prime number is. Give me one.
7.
7. See, so 7 is a prime number because it has two factors. What are its factors?
1 and 7.
1 and 7, that's it. Right? Only two factors, 1 and 7. What's another prime number? 13. Two factors, 1 and 13. Are there any prime numbers that are even? Two. Emily's right. There's one. There's one prime number that's even. It's the number 2 because it has the same property, right? 2 and 1. 2 times 1 is 2. So 2 and 1 are its only prime factor, only factors of it. All right. So we've given us several examples. So 2, 13, 7. There's lots of them. All right. Composite number is any positive integer. Notice we're still doing positive integers. The only reason you're not seeing the word whole number used is because we're not talking about the number 0. Okay, so we have to go from 1 and up. So we could say natural numbers. Your book is using the word positive integers, but natural numbers are counted numbers as well here, right? All right, composite. Any positive integer with more than 2 distinct factors. Give me an example. 6. So let's just do 6 for a moment, and we'll do 8 in a sec. So in example 6, what are the factors of 6?
1, 2, 3, 6.
So this one actually has 4 factors. And 4 is more than 2. Today and tomorrow it is. Let's do 8. What are the factors of 8?
2, 4, 8.
So there's a way to get 4 factors. Is there any way to get 3 factors? 4 will work, yeah. So what are my factors of 4?
1,
1, 2, and 4. All right, so we've got lots of composite numbers. We have lots of prime numbers as well. So, yeah, we can create these guys. At least we can create the composites anytime we'd like. Prime numbers are not able to be created in that sense. But are there any numbers that are positive integers that are neither prime nor composite? 0 is not a positive integer. 1 is a positive integer. So the issue is 1 in either of these categories? What are the factors of 1? 1. So how many factors does it have? 1. What does it take to be prime? 2. What does it take to be composite?
2.
So yeah, 1 is not prime and it is not composite either of those cases, okay? It's important to remember because we tend to sort of gloss over that sometimes when we think about this. And I don't know if we'll get there today or not, but there's one example at the very end that talks about why we can't have it be prime. We want to say it's prime. And so we're going to talk at the end about why we can't have it be prime to make everything else even true. We need to be true to work. All right, factorization. We use the word factorization, but most of the time when we use it with the word prime in front of it. So let's just talk about what factorization is first. So all factorization is any expression of a number in some factored form. Okay? So it doesn't have to be factored down into primes, but in some factored form. So let's do an example. Give me a factorization for 12.
4 and 3.
Okay, 4 and 3. That's what I said 2. So 4 times 3 would be a factorization for 12. Is it the only factorization for 12? No, what else could I do?
2 and 6.
I could do 2 times 6.
1 and 12.
Sure, I could do 1 and 12. Whoops. Yeah, using only positives. We're not going to be using negatives. What if I did 3 numbers? Could I do a factored form with the 3 numbers involved? Sure. I could get even more creative and I could do something like this. And it would work, wouldn't it? because there's all these different ways that I can write it in factored form, we need something that's more specific, and so that's actually why we see prime factorization used more than factorization. So if you went in or if I went in and talked to your class or whatever, and you were talking about factors in class, and you do this when you talk about division. So we're talking 3rd grade, right? They learn about division in 3rd grade, they talk about factors of a number, okay? So very quickly, some children start to figure out that 12 is not just 3 times 4, 12 is also 2 times 6. So if you went into a class and said, what 2 numbers multiply together to give you 12? Well, these 2 kids over here are going to say 2 times 6, and a couple of them in the back are going to say 3 times 4, and there's a few of them that are going to say 1 times 12, and everybody has different answers, and they may all be right. So we need something that's more specific so that we have the same description when we talk about it, and prime factorization does that for us, okay? So prime factorization is a factorization that contains only prime numbers, and I have one of those up there that has that property. Which one of those is a prime factorization for 12? In every other case, I have a multiple, or sorry, I have a factor in there, some number that is not a prime number. Whether it's 1 or 6 or 4, whatever, I have another one in there that's not prime. It's either composite or it's the number 1. This is the only one that's the prime factorization. So I want to show you 2 ways of finding prime factorizations. Okay, one of them I know you've seen before. Your book outlines it, and it's the one that's most commonly taught, at least across curriculums that I've seen, and that's factor trees. So raise your hand if you've seen a factor tree. Okay, have you seen it before, Sarah? I think you probably all have, even if you're not sure right now. I think when we do it, you'll see it. So we're going to do a factor tree because it's a familiar idea. It's a good method. And then I'm going to show you another method, and we're going to talk about kind of the benefits versus the maybe shortcomings or whatever, the things where the other one's not quite as good at it. So the first thing is the factor tree. So with a factor tree, you have a lot of flexibility, right? So you can pick any 2 numbers that multiply together to give you this. So somebody pick a number that you know that's going to divide this. 10 is really nice, and we know it's 10 because it ends in a 0. So if I put a 10 here, what do I do next? All right, and so this is 2, 3, 6, 6, right? And then I keep going. And I'm going to keep going down this process until I end up with primes at the end of my branches. So what is 10? 2 times 5. What am I going to do now with 20 through 66? Divide it again. What do you want to divide it by this time? 3. I don't think 3 is going to work. 2 will. So if I divide it by 2, what do I get? 1183. Yeah, 1183. Okay, so 1183. Yeah, that's right. Yeah, it's 1183. 2s aren't so bad to do in your head.
Don't make me feel bad about something.
All right, that's good. If you want to do it 3s, then you're very impressed. Right? 1183. Now what?
Divided by.
So 2 doesn't work. 3 doesn't work, 5 doesn't work. Well, 7? We don't have a divisibility test for 7. There is one, but your book doesn't present it, so we haven't taught it. Grab a calculator. Grab a calculator out, please. This may test. Will it divide by 7?
Yes.
It will divide by 7. What will it become, Lauren? 7 and what?
169.
Okay, now 169, again, is also not prime.
Divided by 3.
3 won't work.
Why?
Because it won't.
I want to say
13 is correct. 13 times what?
1. Nope.
Times 13. 169 is one of the perfect squares, right? 13 times 13. I don't know how far you memorized it when you did squares. I think typically 12. I say I've seen 15 in some curriculums. They'll go up to 15 where some students memorize their 15 squares for whatever reason. I think it's probably 13 as high as I know. I mean, just off the top of my head. I'm not thinking what 14 is. That may be right. 15 is, what's 15 times 15? Yeah. What is it, 625? 225, rather, 225 now. Okay.
You
All right. This is a factor tree. Okay, so it's got a lot of flexibility because you can do the divisions in any order, and it's got that going for it. One of the things that you have to be careful of when you do a factor tree is not losing the end of any branches. And I know that sounds sort of elementary, but the issue is really that if you're not being really careful, it'd have been really easy to omit the circle for the 2 here. Because I had so much more going on below it, it would have been really easy to just overlook it. You have to be a little bit cautious when you get to the end that you don't actually overlook a portion of this. Now I need to talk to you about how we write our solution though. It says find the prime factorization. Well, we've got 3023, 660, and this is a 2, and how many 2's are there? 2, so that's 2 squared. And then you would write the next highest factor after 2. What is there in this? There's a 5. How many 5's are there? 1, so we just leave it alone. We're going to put a dot between them here. And then what's the next lowest after 5? 7. And this is the dot. And then I have, and there's only one 7. And then I have 13 squared. So the question is, are we going to multiply them? Actually, if we did multiply them all out, we would get back to the 23, 660 we started with. Okay, that's what factors are. Factors are a division representation with the dots between them, showing the multiplication portion of it. That would multiply back out to give you the original number. Okay, so this is factor trees. I want to show you another method that is, I don't know when I ran into it, but I've seen it taught in some books and not in others. So
That's the answer.
that is the answer. That is the prime factorization, yes. All right, so let me show you another one. This method is going to look kind of like a division method upside down. Upside down. And what we're going to do is we're going to look for the smallest prime number that divides this number. And what is that? 2. All right, so Lauren, since you are so good at dividing by 2, can you divide that one for us?
11830.
That's right. All right, so that's what we have. We do it again. The smallest prime number that divides it would be 2. All right.
5915.
Yes. 5915.
How do you do that?
Huh? Well, because you either get, it goes in evenly or it doesn't, right? So 2 goes into 11 5 times. So you write down the 5, and then you have that leftover 1 in the A. Then you've got 18 is 9, so that went in evenly, so you're done with those pieces. 3 goes in 1 time, and then you've got 1 left over, 1 and 0 is 10. It's a lot harder when you're working with non-2s because you don't always get just 1 as a remainder or 0 as a remainder. That's why 2s are max.
Oh.
All right, 5915.
5.
We'll divide by 5.
11830.
Yes. All right, 1183. We've already seen 1183 once today. So that would be 7 next. That's my next smallest number. It divides by. It is. That is right. And then 13 and 13, right? So this method is a little bit more structured, right? You have a little bit more rules involved. You're only looking to divide by primes, whereas over here I can divide by anything. I just stopped when I got to the primes. The other nice thing, the structure thing is a nice or not nice depending on your personality, I think, but kind of the nice thing is that all the factors are on the edge. So overlooking one of them doesn't really happen like it can happen over in the factor tree method. The other thing that's nice is that the ones that go together are beside each other, right? You see the 2 and the 2 and they're right beside each other. I don't have to look for another 2. The 3 is by itself, not 3, sorry, 5 is by itself, 13 are beside each other. So I was teaching this in another class the other day, and what I was likening it to, and I think that this is a pretty good description, is you guys have all been in comp or you took an English class in high school, right? Okay. So what I remember from when I was first doing writing essays and whatnot like this in high school is that there was these 2 sort of brainstorming ways of thinking about things. One was this idea of doing cluster diagrams or bubble diagrams where you have all these different things and you drew lines between them and it looked like this. And the other way, sort of in competition with that, was this idea of an outline form, right? Had more structure, had more details, And so it really depends on how you think as to which one sort of, calls to your heart and says, do this one, right? Do you think sort of like this, right? Or do you think like this? I mean, how do you think? And so I don't care which one of these you use. It makes no difference to me whatsoever, but I wanted you to see them because the reality is that some of your students probably aren't going to think like you. And so I'm not going to impose my thinking upon that either. I tend to think which one? Yeah, the really structured one. That's how I think. That's probably why. So I tend to think very linearly, very step by step. This is what I do first, this is what I do second, this is what I do third. The times when I get overwhelmed are from like English when I've got this big mess of things. This is why I write to-do lists. Because it helps me to make sense of what I'm talking about.
And then your
Otherwise, I feel overwhelmed. My husband just can't know. It's
So, on the test,
yes,
on the test, are you going to ask us for either one of those?
Yeah, you can do whatever. It'll just say this blood directions in here, find prime factorization.
Okay.
You have to show something. You have to show.
But you're not going to ask for a specific one?
I won't, no. All right, now these are a little different, B and C, because they sort of look like they're already a little bit factored, but they're not in the form they're supposed to be. What's wrong? Say that again, Lauren? They're not prime. Not all of them anyway, right? Okay, so some of them that you see here between B and C, they're not all prime numbers. So what do we do with this? Well, we don't need any factor trees. We don't need anything like that, okay? Because the numbers are small enough to handle. So if you think about this number 16, I suppose you could do a factor tree for each of these if you want. But what is 16? We'll do one. 16 is what?
4, 4.
4 and 4. And what is 4?
2, 2.
2 and 2, and we have to do it twice. So when I'm rewriting this and thinking about this, I'm not going to write 16. I'm going to write 2 to the 4th. And then remember the original problem here had a 4 right there, so it needs to still have a 4 on the outside. 2 to the 4th is 4. We're going to simplify that a little bit to hold tight. Well, I replaced the 16 with 2 to the 4th, and then this 4 was already still here. We need to do the same thing with 81. 81 is 9 and 9. 3. So how can I rewrite 81? 3 to the 4th, and it happens to have another one to the 4th over there, so that's good. 6 is easier. 6 is 2 times 3. Again, to the 6th on this one now, right? Okay, so what we're going to use next is we're going to use the properties of exponents that we talked about back in chapter 3. We talked about in chapter 3 linear multiplication. So what happens to these two exponents? How do I combine them? You do. You multiply them. So this is 2 to the 16 and 3 to the 16. What do I do over here? Because this is different. 2 to the 6th and 3 to the 6th. And yeah, there's really supposed to be dots between these, just like your language is indicating. Is it done? No, because it can be simplified. How many 2's do I really have here? 22. So this is 2 to the 22. And how many 3's do I have here? It's also 22. So the complete factored form is 2 to the 22 to the 22nd times 3 to the 22nd. You know, C is different. C doesn't have any, I mean, they are all primes. They're 2, 3, and 7, right?
Yeah.
But I don't have this in factored form because there's addition involved. Okay? All right, so do you remember we did something called the distributive property?
Yes.
What we're going to do here is we're going to undistribute. Okay? I.e. factor. That's what it's called. Look at 2 to the 2nd and 2 to the 4th. What do they have in common?
2.
More than 2. They have 2 to the 2nd in common. Right? Just one of them says 2 to the 2nd. Okay, fine. The other one says 2 to the 4th, but 2 to the 4th is actually 4 2's.
Yes.
The first one has 2 2's, 2 squared. The second one has 4 2's, 4 squared. So they have 2 2's or 2 squared in common. Okay, so I'm going to pull that out in front for the moment. How about the 3's? How many 3's do they have in common?
4.
There are 4, because there's 4 on one of them and there's 5 in the other. So they have 4 in common. So 3 to the 4th. How many 7's do they have in common? All of them. 55 of them, that's right, all of them. Now, pulled out what they had in common, but that means there's some things that they didn't have in common that are left over. So look at the first one. 2 squared, well, I pulled all of that out. 3 to the 5th, and I pulled out 4 of the 3's, which means what's left? 1, 3. 1, 3. Yes?
Wait, I thought there were the 2's. For like the 2 to the 4th, isn't it? 2 squared, 2 squared. So when you have another 2 squared.
We will when we get over here. We aren't there yet.
Oh, okay.
We're still just working on this first
Okay,
piece.
that's,
Yeah, the first piece only had a 2 squared in it, so I don't have any of those left.
okay.
The second piece has a 3 to the 5th, which means I pulled out 4, and I have 1 3 left. How many 7's do I have left? No, I already pulled them all out, right?
It's 77.
Yeah, you have written 77.
Oh, why did I write 77? I'm sorry.
Maybe because you wrote 55.
Maybe so. Okay, that looks better. Thank you. Okay, so I have a 3 left. I have an addition sign. It needs to stay here as well. Now let's do what you wanted to do with the 2's, Caitlin.
Okay, how come, like, there's one left over?
How come there's only 3 left over?
Yeah, I don't see how
Okay.
you got that.
This 3 to the 5th right here means I have 5 3's, and I only pulled out 4 of them.
Why?
Because there's only 4 of them over here that match up.
Oh, okay.
Oh, I got you.
Yeah, it's like matching.
It's all coming together.
It's all coming together. So I'm
Okay.
looking for what they have in common. And that's all I can pull out in front of what they have in common.
Okay, then why'd you only, okay, never mind, never mind.
Okay?
Ask me a question.
Okay, so are we all right?
Yeah.
Okay, now we're only half done in the sense that I still have another piece inside this parentheses here. So now we're on to this piece right here. 2 to the 4th, there's 4 2's. How many did I pull out in front? 2 2's, which means how many 2's are left? 2 2's. So this is 2 squared left right here. That's a 3 to the 4th. That's 4 3's. How many 3's did I pull out in front? 4 3's. So are there any of them left? No. How about my 7's? No, there's none of them left either. Okay, so take this then. So this is 2 squared, 3 to the 4th, 7 to the 55th, 3 plus what? 4. What is 3 plus 4? 7. So this is 2 squared, 3 to the 4th, and 7 to the what? 56. Add 55 to go, now I have 1 more when I got my factoring, whatever. So I have 56 of them now. What these problems really do is they really force you to remember your distributive rules, your commutativity rules, your exponent rules, right? All those different properties of exponents and multiplication that we've had, and addition, that we had back in chapter 3. Really is pulling heavily on chapter 3. Okay. All right, we are going to stop here.